After we learned the power function, we need to extend this to polynomial. You know what the polynomial is made of. It's made by a constant, a linear function, a quadratic function, and each of these are a power function. Give you an example. See, that's a cubic function. And each of these are made by 1, 2, 3, 4 of the power function, include the constant that you can think as x to the 0 power. Now we can define the polynomial of a square matrix. What you are doing is instead of look at number, this time your capital X is an n by n dimensional matrix. And the I is the n by n identical matrix. And then we're going to define this polynomial as follows. This will be a nth degree polynomial. Well, let's check if it makes sense in the first place. When you add two matrices, what is the condition you can add? Like A add B. They must be exactly the same dimension, right? Otherwise, you cannot add. At 2 by 2, you add 2 by 2. 3 by 3, add 3 by 3. So here, I is n by n. This is a scalar, x n by n. X squared is n by n. X n minus 1 is n by n. Each of them is n by n matrix. When you add together as the result of the polynomial, of course, it's an n by n matrix. It's just a table. How many elements? If n equal 10, 10 times 10, you have 100 numbers, right? That's what we are doing. That's why it's powerful. But in scientific computation, you can easily get thousands. The n is thousands times 1,000. But you're going to do the same computation we're going to show you today. So let's look at the diagonal matrix again. If you have a hard time to follow abstractly, then let's make this number to make it easy for us. So it's a diagonal matrix. And if you want to square that, then you know it's going to be 4, 9, 16. Everything else is still stay 0. And the q, then you got a little bigger. Let me see, what's the q? Anyway, the bottom line is everywhere else except this diagonal is 0. Keep that in mind. That matter is power or polynomial. So if I have a diagonal matrix, I want to consider this polynomial again to the lambda q plus 3 lambda squared plus 2 lambda plus I. What I do? I just need to add all those power polynomials, right? So again, you only need to consider this element, which is the position 1, 1. And the second element is position 2, 2. The third element, position 3. So what are those elements? That's nothing more than you plug in your lambda, in this case 2, to here. So in my example, let me call it example 2. I'm going to put the first element in here as 1, 1 is going to be 2 to the q, 3 times 2 squared, plus 2 times 2 plus 1. What is that? 8. Plus 12 plus 4 plus 1, that's 25. See? So your result of this is going to be 25 here. And the second element, 2, 2, you're going to get a 3q plus 3 times 3 squared, 2 times 3 plus 1, 27 plus 27, 6 plus 1, 51. So the second element is 51. The last one, let me see, 3, 3, you're going to do it 4q 3 times 4 squared plus 2 times 4 plus 1. That'll make a 9, 16, 48 plus 64. Can you add by mind? Is going to be 112, then plus 9, 121. Then that's how you calculate a polynomial. I can calculate just by hand. So you see the advantage of this diagonal matrix. So the observation is you only need to calculate the element in the diagonal. Anywhere else is 0. So it is not limited to 3 by 3. You can extend to any matrix as long as it's a square. That means n by n. And it can reduce the computation significantly because you only look at the n element instead of n by n, right? If n equals 100, then instead of calculate 100 times 100 polynomials, you only look at the 100 polynomials. What does that mean? That's 1% of computation, right? The advantage is 1% of the computation if the dimension is 100. So how about if the matrix is not diagonal? Well, we'll say make it as a diagonal. But how? We make it by so-called eigen decomposition. This is the last concept for today. The eigen decomposition, you need to first get the eigenvalues and the eigenvector. We know how already from the previous hour. So if A is an n by n matrix, and the bottom line is not defective. What it means not defective again? Means you can find exactly n eigenvectors are linearly independent. If you say, oh, I found the n, 1, 2, 3, that does not count. That's dependent. Just count as 1. But if you have 1, 2 like that, that counts as 2. If you can find the n of them independent, you're good. It's not defective. If anything is not defective, you can always write it as this form. Q is a square matrix made by all the eigenvectors. So the reason I wanted it to be linearly independent because I wanted this Q inverse exist. In another word, this Q is not going to be singular because they are independent. What is in the middle? The middle denominator, capital letter, is the eigenvalues. The D, if you use the MATLAB example before. So any matrix A can write as Q, the eigenvectors, made all n of them, and the Q inverse on both sides, and the Q inverse, like that. So let's see what advantage we can take.